For our final section in Unit 1, we are in Chapter 6, Section 10, talking about functions and their graphs. We're going to focus a lot on domain and range. This is a topic that the four-year universities you guys transfer to have requested that we include in this course, and it doesn't particularly fit with any of the information, so we've kind of added it on here at the end of Unit 1. Hopefully, a lot of these definitions are already going to be familiar to you from your high school algebra classes as we talk about functions and their graphs. A relation is our general definition for any set of ordered pairs. Now, when we're talking about sets of ordered pairs, we're referring to a XY coordinate plane graph, a real coordinate plane graph, where we have our x-axis as the horizontal axis, our y-axis as the vertical axis. And let's say I chose to plot a point here. I've moved over to the left 2 units, and I've moved up 2 units. That ordered pair, let's say this is point A, the location for A would be at -2, 2. When you write an ordered pair, it's always an XY ordered pair. The horizontal shift comes first, and the vertical shift on the y-axis comes second. So any set of ordered pairs is a relation. When I plot my points on my graph for a relation, it could be anything. It could look like a squiggle-dee line. It could go back and forth, left to right, up and down. It could be just a set of points. Anything is a relation. When I talk about a function, though, I'm talking about a specific type of relation. A specific type of relation. It's a relation where each x value is assigned only one y value. Each x value is assigned only one y value. So if I plug an x into my equation, I get out one value for y every single time. Another way to say that is that a function is a set of ordered pairs in which no two pairs have the same first coordinate and different second coordinates. The first coordinate is the x value, No two ordered pairs have the same first coordinate and different second coordinates. When we're talking about domain, we're talking about that set of first coordinates. It's my set of x values. The domain is my independent variable. It's what we plug in to get our answer. And our answer comes in the form of the range, which represents the set of second coordinates, or our y values. And that range, those range values depend on the x coordinates, the x value that's plugged in. So these are our dependent variable. The range is made up of the set of the dependent variables. If a relation is a function, it is going to pass the vertical line test. A graph represents a function if there is no vertical line that will intersect or cross the graph in more than one place. This is my vertical line test to see whether or not my relation is a function. If it passes the vertical line test, that means that I can draw any vertical line I want, and a vertical line goes up and down, like a porch post. Vertical line test, my y-axis is my vertical axis, so I can draw any vertical line I want anywhere, and it won't intersect my graph in more than one place if my graph is the graph of a function. Now, we talk about functions as being functional, as working. Our definition was that each input, each independent variable, has only one output, one dependent variable. I want you to consider these three different soda machines. So you go up, you're thirsty, and you want to buy something to drink. Which one doesn't work? Which one has something wrong with it? Well, machine 1 looks fine. If I push button number 1, I can get a Coke. If I push button number 2, I can get a Dr. Pepper. If I push button number 3, I'll get a water every single time. So machine 1 is fine. That means it's one of these two machines that has a problem. Well, hopefully you recognize that machine 2 is the one that isn't functioning correctly. Because if I push button number 2, I might get a Coke and I might get a Dr. Pepper. I don't really like Coke. I like Dr. Pepper. So that's going to be a problem for me if I push number 2 and I'm expecting a Dr. Pepper and I get out a Coke. So this machine isn't functioning correctly. It's not a function because button number 2 is assigned to both Coke and Dr. Pepper. It's not a sure thing. I might push the button and get a Dr. Pepper, but I might also push the button and get a Coke. That's not okay. That's not functioning. Let's look at the next example. Consider these semester grades. Now we've got 3 different teachers that have assigned grades for their students. Which teacher has messed up? Has their grade sheet is not functional? Well, this time it's Mr. Pitt that has a problem. What is going on with Mr. Pitt that has a problem? Well, he gave Mike 2 different grades. That's not okay. If we get to the end of this semester and you ask me how you did in the course, and I said, well, you either made an A or an F. That's not okay. You get to each course, each student makes 1 grade. So that's not functional that he gave Mike 2 different grades. Okay, so in the soda machine example, we had input. What was our input in the soda machine example? Well, inputs represent elements in the domain. And for the soda machine example, we were looking at pushing the button. That was our input. What was the input for, what would you consider the input for this example with the grading? Well, the input would be the student. What about the output? The output represents the elements in the range of our relation. For the soda machine example, I push a button and I got a drink out. So that is, I have an input, there is an output. For the grading example, I give a student name and I get a grade back. In the soda machine and grading examples, which sets depended on the other? Well, the drink I got depends on the button that gets pushed. And the grade that I'm quoted depends on the student that I name. So in these 2 examples, the button I pushed and the students named were independent variables. Those were my inputs. The output I got was the drink or the grade that depended on what the input was. So now to tie our vocabulary together, the x variable represents the domain of my function, which is also called the input or the independent variable. So the input is the independent variable. The y value of my function or of my relation represents the range of that relation. It is the output, and it depends on the input. So it is the dependent variable. There are vocabulary terms for domain and range. Okay, one more time, we're going to define our function. When I have a function, and it says make sure we use the terms input and output. When I have a function, each input has only one associated output. Each input has only one output if it is a function. Now remember, another name for input would be x value, independent variable, independent variable, or first coordinate. When I'm talking about output, I'm talking about that y value, which is dependent, and if I have an ordered pair, it's the second coordinate. Now we're going to start identifying domain and range for these relations and determining whether or not each relation is a function. Now, something I want you to make note of, in the MyMathLab homework, if it's going to ask you, is this relation a function? And if you say yes, it will ask you for domain and range. If you say no, it does not ask you for domain and range, or it lets you say it's not a function. Whether or not a relation is a function, a domain and range still exists. I'm not sure why MyMathLab does the problems that way. It bothers me a great deal. When you get to the test, if I ask you for domain and range, you give me domain and range, whether you determine that the relation is a function or not. It still has a domain and range. Okay, so let's look at these ordered pairs, sets of ordered pairs, these given relations, to determine whether or not they are functions. When I look at number 1, I see that I have 1, 2, 3, 4 ordered pairs. I'm going to look primarily at the first coordinates, those x values for each. Those x values is my domain, they make up my domain. And I see that each of these x values is different. Because each x value is different, I have a function. My domain is the list of values. Now, this is not a continuous function. I'm not connecting these dots. If I put these dots on a graph, they are just 4 individual dots. So when I give the domain, I give it in fancy braces, and I'm just going to list from least to greatest. The lowest of those 4 values is -4, then I have 0, 1, 2. You could have given them in the order they were found, 0, 2, -4, 1. That's fine. I just usually like to go least to greatest. Then range are the set of y values that are assigned to each of those x values. My range includes the values 1, 3, 1, 2. I see that 1 is repeated in the range. That's not a problem at all. When I list my range, I have the values 1, 2, 3. I don't write 1 down more than one time. It shows up in my ordered pairs more than once. I only list it once when I list the range. All right, look at number 2. Determine whether or not this relation is a function. Well, hopefully, as you're looking through your XY ordered pairs and you're identifying the values in the domain, you see that you have 2 ordered pairs that have the same x value. When that happens, you have to look at those y values. My definition for function says that each input is assigned only one output. Well, that's not true in this case. The input 2 is assigned 2 different outputs, 2 different y values. So this is not a function. Not a function because of those 2 ordered pairs. Now when I list domain and range, I do it just like the other problem. My x values are 2, 4, 3, 2. So I list 2, 3, 4. I chose to do it least to greatest. You don't have to. I do not list 2 more than one time. My range is my set of y values, is made up of my set of y values. My range is 11, 15, 0, negative 2. From least to greatest, it would look like that. All right, number 3. Is number 3, is that relation a function? Well, hopefully by now you're starting to look through those x values. You see we have a repeated x value and the y value assigned to that x value of 3 not the same. So that is not a function. My domain would be 3, 6, 12 because those are my x values. And my range would be negative 5, 0, 7, 9 because those are my y values. You guys do the next one. I got it out of order. I didn't do least to greatest on my domain. My pen is skipping. So I have a repeated y value in number 4. Does that mean this relation is not a function? It does not mean that. It is a function because each of my x values is unique and each x value is assigned to only one y value. For numbers 5 and 6, instead of a list of ordered pairs, I'm given points on a graph. I can still answer the question, is this a function? By looking to see whether my x values are repeated. If my x values are repeated, I will have more than one point on a single vertical line. If I draw a vertical line, I would draw through more than one point. That doesn't happen. So this is a function. Well, what's my domain? My domain is going to be my set of x values. I have a point above 1. I have one above 3. I have one at 4, and I have one at 5. What's my range? What are my set of y values? For my y values, I'm looking at how far up they go. So I'm looking at the values on the y-axis. I have 1, 2, 3, and 4 for my range. 1, 2, 3, 4. If I wanted to label the location of these points, this point is at 1, 3. This point is at 4, 4. This point is at 3, 1. And this point is at 5, 2. You guys do number 6. Is number 6 the graph of a function? Well, no, this relation is not a function because when I check my vertical line, I see that I have 2 points that fall on that vertical line. So I have an x value, 1, that is assigned 2 different y values, so that doesn't work. Even though it's not a function, it does still have a domain and range. My domain is 1, 2, 5. My range is 1, 2, 3, 5. Okay, let's look at the next page. Consider the relation that includes each set of ordered pairs. For each, you're going to see if it is a function, graph and connect the points, and identify what type of line it is. All right, well, when I look at A, it asks whether or not it's a function. If I look through my x values, they're all negative 1, so no, that is not going to be a function. Let's graph and connect the points. I'm at negative 1 up to 5. 1, 2, 3, 4, 5. Negative 1, 2. Negative 1, 3, negative 1, 4. So 4 points right there. If I connect those points, I have formed a vertical line. It is not a function. It is the vertical line test, isn't it? They're all on one vertical line. Okay, what about B? For B, when I look through all the x coordinates, they're all different. So that looks like, yes, that is a function. B is a function. What kind of line is it if I connect the points? So let's plot the points. 1 over 1 up 3, over 2 up 3, over 4 up 3, over -6. 1, 2, 3, 4, 5, 6 up 3. If I connect those dots, what kind of line do I have? I have a horizontal line. Okay. When does a graph represent a function? Well, a graph represents a function if you can draw a vertical line on the graph. Oh, I didn't read my sentence well. If you can draw a vertical line on a graph and it touches 2 or more points on the graph, it is not a function. So that's how it fails the vertical line test. This one's a function, it passes the vertical line test. This one fails the vertical line test. It is not a function. So we're going to use the vertical line test to check and see whether these problems are functions. So I've got a parabola shape on its side here. I can draw a vertical line. It hits in more than one place. It is not a function. What about number 8? I could draw any vertical line I wanted to draw, and it will only ever cross in one place. That is a function. Number 9, also a function, passes my vertical line test. What about 10? 10 fails the vertical line test because I can draw at least one vertical line where it goes through the function, or through the relation, in more than one place. Number 11 is that horizontal line. Yes, it is a function. It passes my vertical line test. This is the line that has been graphed right here. This is what I'm asking about. Is that a function? No. In fact, it is the vertical line, so it definitely fails the vertical line test. Let's focus a little bit on practicing our domain and range. For these graphs, these relations, we're going to determine whether or not they're functions and then identify the domain and range. And we're going to use an inequality symbol to do that. Okay, we're going to use an inequality symbol to identify the domain and range. What about number 13? Does it pass my vertical line test? Yes, it does. It is a function. Now I see that this wave on number 13 has a specific starting place and it has a specific ending place with filled in dots. If I'm looking for domain, I'm talking about the x values it covers. So I'm interested in the length of the x-axis that is included. Well, what are my x values for this domain? The first x value is 0, and the function keeps going until I get to the x value 7. So my domain is going to be the set of x values from 0 to 7. Now you see what I did there. I put the x in the middle, I put the lower limit on the left, and the upper limit on the right. So all x values from 0 inclusive to 7 inclusive, because it has that or equal to line underneath. Now for range, I'm interested in the set of y values. So I'm not going to use x, I'm going to use y. And I'm looking at my y-axis. So if I start down here low, I see my function doesn't pick up any y value until I get to -2. So my function starts at -2, and then it exists up until this y value 4. So the least y value for my function is -2, and the greatest y value for my function is 4, and it's a continuous curve. So I'm going to find every single y value in between. So again, I have my compound inequality statement, y this time because it's range. The least value, the lower limit, is -2. And the greatest value, that upper limit, is a +4. You guys try number 14. Use the vertical line test first. Is that a function? Well, no, that is not a function. It fails the vertical line test. But it still has a domain and range. Remember that. On MyMathLab, it won't make you give the domain and range when you say, no, it's not a function. On the test and written work, I will make you give the domain and range. I'm going to pause my video and answer this question. You pause yours and do the same. Okay, hopefully your answer matches mine. Domain is the set of x values. As I look at my x-axis horizontally, I start over here at the lowest -∞ x value and I move this way. I see my function first starts when I get here. My function exists for every x value until I get here. So that is the domain of the x values of my function, from -2 to +2. Lower limit to upper limit on the x values, the domain. Now I'm going to look at the y values, the range. Again, I start at the bottom and I think, okay, where does my function start? Well, it starts right here. And I can find my function. It exists for every y value until I get here. So the lower limit for my y values is -4, and the upper limit for my y values, +4. Okay, so let's look at number 15 and 16. Note the difference between the ones we just did. They ended in filled in circles, but on 15 and 16, they end with arrows. Those arrows mean that it just keeps going forever and ever. So the first thing we're going to do is check our vertical line test to check for 15 and 16 whether or not they are functions. Well, 15 passes my vertical line test. It is a function. 16 passes my vertical line test. It is also a function. Again, keep in mind that whether it's a function or not, it does still have a domain and range. My domain is my set of x values. Because this function has arrows on the end, that means it just keeps going. Now, it keeps going down really fast, but it's moving out. If you look, you see that is not a vertical line. It's just that it's moving down a lot faster than it's moving out. It is still moving out, however. So if it goes down forever, that means it's also moving out forever, which means my domain includes all possible real x values. And I believe on MyMathLab it gives you the choice of all real numbers. It might possibly show you parentheses from -infinity to +infinity, but I think it just says domain all real numbers. The range has a limit. It goes down forever, but it doesn't go up forever. You see, my range has a highest possible value. It's going to go down forever, but it reaches the highest point. The highest point is at 10. So my range is going to be all y values less than or equal to 10, because 10 is as big as it gets, as high up as it goes. Now let's look at 16. For 16, I have what we call a parabola. Again, it goes up really fast, but it's still going out. It's not vertical. So it's going to go up, 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 up forever. It's also traveling out forever. Since it travels out forever, the domain, again, is all real numbers, or from -infinity to +infinity. The range this time goes up forever, which means it has a lowest possible value. The lowest possible value we have is -6, and then everything bigger than that, everything above that. So my range is going to include y values greater than or equal to -6. So pay attention to which inequality you need. If you have one boundary, then it's going to be either less than or greater than. If you have ends both directions, an upper and a lower boundary, then you have a compound inequality. Okay, we have one more page. We have 4 more relations to determine whether or not they are functions. I want you guys to pause your video, do this as best you can. I'm going to do mine, and then come back and we'll check and compare our answers. Okay, let's talk about these results. 2 of these relations are functions, 2 of them are not. Number 17 fails my vertical line test, and number 20 fails my vertical line test. But 18 and 19 both pass the vertical line test. They are functions. Whether or not it is a function, we still have a domain and a range to identify. So let's look at domain and range for 17 and 18. For domain, I'm looking at all possible x values. So I start over here at the x-axis where -infinity heads towards, and I move to the right just like I'm reading a book. Well, I see my function starts right there when I get to -4. And these arrows on the end means it just keeps going on and on and on and on forever in this direction. So the lowest value of the domain is -4. I have x values greater than or equal to -4. As this parabola shape that's laid on its side travels to the positive direction of the x-axis, it gets wider and wider and wider. So as that widens for infinity, it's going to include all possible real numbers in the range. Number 18, I have a limit on my x-axis. As I travel across the x-axis from least to greatest, from left to right, I see that my function picks up here where x is -2, and I see by this arrow that it keeps going on and on forever in that direction. So my limit on my domain is a lowest value of -2, x values greater than or equal to -2. Then on my range, my y values, I start down here at the bottom at -infinity and I work my way up. And I see that my function starts at the lowest possible value where y is -1. And it just keeps going. Now it's fairly flat, but it is going up. So as I go to positive infinity over here on my x-axis, my y value is increasing forever as well. So I have y values greater than or equal to -1 as my range. 19 and 20 have limits, upper and lower limits, for both domain and range. 19 looks interesting because I have the same limits but for different directions. On my range, as I move from left to right, I see that my function first starts here at x is -4. My function exists for every possible x value until I get here to where x is +4, and then that's when my function stops. That's my domain for that function. For range, I use my y-axis and I start down here at -infinity, and I see my function first starts here where y is -4. That's the first place I see my function exist. And my function exists all the way for every y value until I get to +4 on my y-axis, and that's where I see my function stop. So that gives me my limits on my range. On 20, I have an oval or an ellipse, and I follow the same procedures, moving for my domain from left to right. I see my ellipse first has a value at -4 on the x-axis, and I can go and find my function for every x value until I get to +4. So there is the domain of this function. For the range of this function, I start down here at the negative values on the y-axis. I work my way up, and I see my function first starts here where y is -3. And my function exists for every y value until I get to +3. And then I don't have any more above that. So those are the limits on my range.